How's it going, accelerated chemistry students? This is Mr. Spurk, and this is your Chapter 10, Section 1 notes, all over describing chemical reactions. So let's first talk about chemical reactions in you. After a meal, a series of chemical reactions take place as your body digests food. Plants use sunlight to drive the photosynthetic process needed to produce plant growth. And all chemical reactions involve changing substances. One or more reactants change into one or more products. So let's talk about word equations. The reactants are written on the left and the products are written on the right. An arrow separates them, and you read the arrow as yields, gives, or reacts to produce. So this is what it's going to look like. Reactants on the left, an arrow that tells us yields, gives, or reacts to produce, and the products written on the right. So how could you describe the rusting of iron? Normally somebody would say iron reacts with oxygen to produce iron 3 oxide, or rust. But the way we would write that as a word equation is iron plus oxygen yields iron 3 oxide. Notice that no plus sign is needed on the product side, and that's because iron 3 oxide is the only product. The production of a new substance, a gas, is evidence of a chemical change. So here we could have hydrogen peroxide, which yields to produce water and oxygen, and we know that oxygen is a gas. The burning of methane, the burning of methane is a chemical reaction. We have methane plus oxygen yields carbon dioxide and water. So chemical equations. A chemical equation is a representation of a chemical reaction. The formulas of the reactants are connected by an arrow with the formulas of the products. Chemical equation for rusting that we just talked about is iron and oxygen yielding iron 3 oxide, or Fe plus O2 yields Fe2O3. A skeleton equation is a chemical equation that does not indicate the relative amounts of the reactants and the products, and a skeleton equation is the first step in writing chemical equations. To add more information to the equation, you can indicate the physical states of substances by putting a symbol after each formula. Parentheses S is solid, L is liquid, G is gas, and AQ is aqueous, when what that means is just a substance that's dissolved in water. So the way the rust equation would look like is Fe solid plus O2 gas yields Fe2O3, which is a solid. In many chemical reactions, a catalyst is added to the reaction mixture. A catalyst is a substance that speeds up the reaction but is not used up in the reaction. A catalyst is neither a reactant nor a product, so its formula is written above the arrow in the chemical equation. So here we have hydrogen peroxide, which is aqueous because it's dissolved in water, and we have MnO2 as our catalyst, so we write it above the arrow, which yields H2O, which is a liquid, and oxygen, which is gas. So here's some symbols that we're going to use in chemical equations, and we've talked about most of these already, but we have the plus separates two reactants, yields is our arrow, we have solid, liquid, gas, aqueous, and then we have heat, which is that little delta sign, or you can just write the word heat. These are going to be the most common for us in this class. So chemical equations, let's try one out. Hydrochloric acid reacts with solid sodium hydrogen carbonate, or sodium bicarbonate, and the products formed are aqueous sodium chloride water and carbon dioxide gas. So let's write a skeletal equation for the chemical reaction. So we know that hydrochloric acid is HCl, and HCl is a solution, so that's going to be AQ, and we're adding sodium bicarbonate to that, which is NaHCO3. And we know that NaHCO3, or baking soda, is a solid. And that yields to give us, which we can look back at our problem, tells us it gives us aqueous sodium chloride. So NaClAq plus water plus carbon dioxide gas. And there we go. That's our first chemical equation. So now we want to talk about balancing chemical equations. How would you write a word equation for the manufacture of bicycles? So if we think about bicycles, we want to simplify that task down and limiting ourselves to the four major components. So we have frames, wheels, handlebars, and pedals. And if we think about a bike, we have those four things combining, which yield a bicycle, right? But the problem is that this equation doesn't tell us how many of each piece we need. So if we think about the equation of a bicycle and we add these things up, we know that a bicycle has one frame, which we'll say is F. We need two wheels, one handlebar, and two pedals. So that's what the equation of a bicycle is going to look like. So if we try this out and write this equation, we have one frame plus two wheels, and that 2 is our coefficient. Two wheels plus one handlebar plus two pedals yields a bicycle. So if you notice, we have everything balancing out. We have one frame, or F, on each side. We have two W's, or wheels, on both sides. We have one handlebar on each side, and we have two pedals on each side. So this is a balanced chemical equation. So these numbers are called coefficients, and they're small whole numbers that are placed in front of the formulas in an equation in order to balance it out. The number of each part is the same on both sides after we balance an equation. A chemical reaction is also described by a balanced equation in which each side of the equation has the same number of atoms of each element and the mass is conserved. As reactants are converted to products, the bonds holding the atoms together are broken and new bonds are formed. The atoms themselves are neither created nor destroyed. They are merely rearranged. In any chemical change, mass is conserved. So let's try another one. When hydrogen and oxygen are mixed, the product is water. So we're going to start out with hydrogen, which is H2. And we're going to add that with oxygen, which is O2. And we mix those together, and that yields H2O. But if you notice, we don't have the correct number or a balanced equation here. If we look at the left side, we have two oxygens, and we have two on the right, or only one on the right, I'm sorry. We want two on the right. So to do that, we're going to add in a coefficient. So now we have two oxygens on the right and two on the left. But if you look at that, we also altered our number of hydrogens. So we take that 2, multiply it by the subscript 2 in the hydrogen. So now we have 4 hydrogens on this side. So we have 4 hydrogens and 2 oxygens. And on the left side, we only have 2 oxygens and 2 hydrogens. So to fix that, we can add a 2 here. And now on this side, we have 4 hydrogens and 2 oxygens. So now we have a balanced equation. So here are just, excuse me, I am okay, I promise. It's just a summary of our rules for writing and balancing equations. So if you just want to look through those, you can write them down. But like I said, these are a summary of everything that we've already talked about. So let's try balancing these chemical equations. We have silver nitrate plus copper yielding copper nitrate and silver. So what we want to do when we have polyatomic ions like that nitrate there, we want to start by trying to balance those out, and we balance those by a whole unit. So if you look on the right side, we have NO3 in parentheses with a 2 outside the parentheses, which tells us we have 2 nitrates. And on the left side, sorry about that, we only have 1 nitrate. So let's go ahead and add a 2 here. So now we have 2 nitrates on the left and 2 nitrates on the right. But that 2 we just added altered our number of silvers. So now we have 2 silvers on the left and only 1 on the right. So what we're going to do is we're going to add a 2 here. So now let's check everything. Let's start on the left side. We have 2 silvers on the left and 2 silvers on the right side. We have 2 nitrates and we have 2 nitrates on the right. We have 1 copper on the left and 1 copper on the right. So this is another balanced chemical equation. All right, let's do another one here. So we have aluminum plus oxygen yielding aluminum oxide. So what we want to do here is let's start by balancing our aluminums. We have 2 on the right and only 1 on the left. So let's add a 2 here. But now, if you look at the O2 we have on the left, we have an even number of oxygens on the left. So no matter what coefficient we put there, we need an even number. But on the right side, we have a 3, which is an odd number. So let's make that an even number by multiplying this by a 2, which will give us now 6 oxygens on the right side. So then we're going to put a 3 here to get 6 oxygens on the left. But now, once we put a number, we might need to change them again. Because if you are adding these up in your head, now we have 4 aluminums on the right and only 2 on the left. So what we can do is we can erase that guy there and just go right back, and we know that now we need 4 on the left. So if we look at adding this all up together again, we have 4 aluminums on the left, 4 aluminums on the right, 6 oxygens on the left, and 6 oxygens on the right. So as a quick review, to write a skeletal equation, we write the formulas for the reactants on the left side of the yield sign and the formulas for the products to the right. After writing the skeleton equation, use coefficients to balance the equation so that it obeys the law of conservation of mass. As always, all the information on these Google Slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, Resources CD, and PearsonChemistry.com. Have a good night, guys.